the series and then just ask you to use the geometric. So you just have to do all that n-1, turning it into what you need to turn it into. So the homework is not as challenging necessarily as this. Yeah?
You just have to prove it that whether it's not a geometrical series. For the homework, you just have to prove it.
They actually tell you, show that this geometric series converges. But later on in the homework, they give you just a mixture of things. All right? You're not going to have enough today to do all your homework. I'm not going to be able to finish 8.1 today. But. OK, I want to show you something else now. It's still geometric series. Please, make sure you watch my homework videos if you want to get some help when you do the homework, right? Because I work through all this. I show as much detail as I can. Check this out. If we are all familiar with the idea of the real numbers, right? The real numbers are peanut-shaped. Yes. The real numbers, right? Which is the number line going in both directions forever, yes? And mixed in this are all the numbers that you can think of, right? Like, except I is not in there, right? Imaginary numbers aren't in there. So when you look at all the different kinds of groups of numbers there are, there's like the natural numbers, right? Which were like, what, like 1, 2, 3. And then you got into the integers, double struct z, which is like, now you can have negatives and 0, right? And then you can start getting the fractions in there, which we use a double struct q for, which represents all the fractions. I'm just going to put fractions in here. OK? So every number that's in here comes from this group or what? I guess what I'm asking you is there a number in here that's not a fraction? Irrational numbers, like pi, square root of 2. So really, if you look at the real numbers, there's really like two major groups of numbers. There's what we call the rational, which is basically your fractions. And another major group, which are your irrationals, which is everything that's not a fraction. And there's actually a lot more of these than these. It's hard to explain, but there's more of these guys than there are fractions in there. A lot of people believe that if I just pick a number out of here, that it's got to be a fraction, that there's always a way to write a number as a fraction, but it turns out that's not the case. Not every number can be written as a fraction, yes?
So you could use the space analogy, that help me.
Yes, I could use that. You want me to use that? I don't want to get too deep into it because I just want to get to my point, which is to try and figure out with the fraction. Yeah, let me get to this. If you want to talk more about that, you can come to my office and I'll talk about that. Okay, so look. Fractions. If I take a fraction, pick anything I want. I'm going to start pretty simple. I should be able to represent that as a decimal. And in this case, it would be just what? 0.75. And this is what we call a terminating decimal. It stops, right? It stops. There's actually zeros, right? But it stops. And I could take another fraction that doesn't stop. What would be a fraction that wouldn't stop? 1/3? It's an example of one that keeps going, but what? It has a pattern to it, right? There's a pattern to the continuation. All fractions, no matter what fraction you ever pick, no matter what fraction you ever grab, it's got to do one of these two things. It's either going to terminate or it's going to go forever, but if it goes forever, it's got to have a pattern. All right? All fractions have to fall into one of these two categories. Irrational numbers like pi, what makes them irrational is that they never stop as a decimal. They never stop. So I'll say pi is equal to 3.141, and it keeps going, right? But the thing is, it doesn't have a pattern to it. There is no pattern. Y'all with me? or not? I know you're like, what the hell does this have to do with geometric series, right? So if somebody gives me a fraction, I go to my calculator, or I use old school long division, I can get this, right? What if someone gives me this? Can I get back to a fraction? And not that little key on the calculator that looks like this. Fraction, how does it go? No, it goes, how does it go? DF or something like that. It's like decimal to fraction. You type it and it spits out the fraction. Some calculators do that. I'm telling you that if the fraction stops or if the fraction continues with the pattern forever, we can always get back the fraction from it. Let me show you how. First, let's take the easiest case, which is this one. What if the fraction stops? Well, wasn't that pretty easy? I mean, look, this is the tenths place and the hundredths place, right? Yes? So this just means 75 100ths. And if you reduce that fraction, you get what? 3/4. Boom. So if anybody gives me a finite decimal, I can pop out the fraction almost immediately. Yes? Yeah? Okay, how about 1/3? So what if somebody gives me 0.333 forever? And let's just act like we don't know it's 1/3, okay? How could I get that to 1/3? You ready? Here it comes. You ready? 0.3 plus 0.03 plus 0.003 plus 0.0003. Do you agree with this? That's what that is? What's 0.3 written as a fraction? 3/10. What's 0.03? 3/100. What's 0.003? 3/1000. 3/10,000. Yes? Continue. Do you see the pattern here? Do you see this is 3 over 10 to the first, 3 over 10 squared, 3 over 10 cubed, 3 over 10. Wait, did I lose this? I think I put too many. That's what it was. I went too many zeros there. 10 to the fourth. Do you agree with that? Do you see the geometric series coming to life here? I can rewrite this as a sum, n equals 1 to infinity. What number never changes here? The 3. So that'll be kind of like my a, I think, maybe. We'll see. It might have to be tweaked a little bit. 3 is never changing. And then I don't have 10 to the n. What do I have? 1/10 to the n. That's critical that you see that, right? Each one of these could have been rewritten as 3 times 1 over 10 to the first plus 3 times 1 over 10 squared plus 3 times 1 over 10 cubed. Understand? And then if I take this or this or this and I raise them, right? When you raise 1 to that power, it's always 1. So that works, doesn't it? Does that look like geometric yet? Yes and no, right? I mean, it has the right form, but it doesn't have the right power yet, right? Need n minus 1? We can make that happen. So we do this. N equals 1 to infinity, 3 times 1/10 to the n minus 1 times 1/10. And if you want to put this 1/10 in front of that, it doesn't matter. I only do that so you can see that when you put those back together, you get back this. Put a 1 on there. So what's actually the a here? It's 3/10, isn't it? So this is actually sum n equals 1 to infinity, 3/10, 1/10 to the n minus 1. That's geometric, right? That's geometric. A is what? A is 3/10. R? 1/10. I don't need to check that, right? The absolute value of that's less than 1? That's going to converge? What's it going to converge to? That's going to converge to A over 1 minus a tenth, which is 3/10. I bet you it turns out to be 1/3. 9/10, right? And when you flip it, it becomes 3/10 times 10/9, 1/3. Okay. All right. Now that's not very impressive. We all knew 0.333 forever was 1/3, right? Yes? Your homework's going to be something more like this. What would 0.2424 be?
Just put out a fraction.
Give me the fraction that gives you that decimal.
To the calculator.
Using calculus.
I mean, technically, the calculator is using calculus, so.
Yes, it is.
Are you gonna give such questions on the test?
Yes,
So we can double check with our calculator?
absolutely, you can double check. But you can't just write the fraction down. I mean, you have to have the work. So how would you redo this? Like the other one we did 0.3 plus 0.03 plus 0.003. This is a little different though. 0.24 plus, and be careful on this one, 0.0024 plus 0.000024, and then continuing.
Because the 2 and 4 repeating, it's your 2 decimal places.
That's right. The bar goes over both 2, 4. I didn't have to write, I could have just written this. But just to show you the pattern is the 2, 4, I wrote like that. Okay? This is really, what, 24 over 100? Y'all pay attention, this problem gets really tricky, all right? 24 over tenths, hundredths, thousandths, 10 thousandths, plus 24 over tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths. 6 zeros. That's all I really need to know, right? Let's write those as powers of 10. I think it'll be a little easier if we write those as powers of 10, don't you? Which is, let's see, 24 over 10, what? Squared, plus 24 over 10 fourth, plus 24 over 10 sixth, plus, keep going. So look at our powers. Instead of like the last problem where it was 10 to the first, 10 squared, 10 cubed, it's 10 to even powers, right? To even powers. And how do we create even? Sum, n equals 1 to infinity. What's never changing? 24. So I'm going to put that out here. Maybe that's too much. I won't go that far. 10 to what power? 2n. 2n. That's how we create evens, right? Which now, can I do this? Did anybody have a question on how I did that?
8.1?
Pardon?
That's 8.1.
What is? What, how do you go from here to here? Yeah, that's kind of an 8.1. How do you create the even? That's what you're saying. Yeah, how do you create an even sequence? Well, that's going to be with 8.1 stuff. All right, can I write this 24 times 1 over 10 to the 2n? Could I do that? Is this geometric? No, why not? It's supposed to be what up there is a power? n minus 1? Uh-oh. Yeah, we can't do minus 1 plus 1 here, because even if we do that, won't it be 2n minus 1? And I need it to be exactly n minus 1. So watch. That's why I said pay attention, because this one's kind of tricky. Is that the same thing? Properties of exponents say that if you have something to a power, you multiply these, right? 2 times n is 2n, so I'm undoing that back to this. So that's actually not, the 1/10, which you thought might be your r, is not going to be your r. It's actually going to be what? 1/100th, right? 1/10 times 1/10 is 1/100th. So we're peeling that 2 off to create the n we need up there. Understand? Yeah, now we can do the minus 1 plus 1. But I'm going to do one more line. You see n equals 1 to infinity. We've got 24. We've got 1 over 100 to the n, changing that red thing into 1 over 100, and then the minus 1 plus 1. Sum n equals 1 to infinity, 24, 1 over 100 to the n minus 1 times 1 over 100. We're almost there, right? 24 over 100 is 24 over 100. I won't even reduce it. Sum n equals 1 to infinity. 24 over 100, 1 over 100 to the n minus 1. That is geometric. We're in business, right? You've got a here. You've got r here. Absolute value of r is less than 1. You're ready to go. So this will become, according to the formula, a over 1 minus r. The bottom. I'm going to still leave this at 24 over 100. 24 over 100 over, what's 1 minus 1/100th? 99 100ths. I tell you about my trip to the coast? I was kidding around with my family. I was like, you know, do y'all want to do like 99 bottles of beer on the wall, right? They're like, no. And so I said, just out of curiosity, how many bottles of beer would we need on the wall if we wanted to like end our trip with a, you know, like end like right about the same time we end the song, we get to where we're going? You know what I'm saying? Like instead of just doing it over and over, like how many bottles would we need? I think I came up with like, it was like 2,476 bottles is what we needed to start with or something. You know? So I just like, I timed it like 99 bottles of beer. I timed it and then I figured out like how long we had to go and what our average speed would be, and then divide it in, and it was like 2,000 something. Why am I talking about this?
Sir, is that your idea of a car activity? You don't play like
I don't know, man. I don't even know what made me think of that, to tell you the truth right now. I guess whenever I get to these problems where it's all just arithmetic at this point, like my brain just starts to go in different places. Like this is just arithmetic, right? Flipping, canceling. 24 over 99. Type it into your calculator. Don't you get 0.24242424? And so something actually pretty ridiculous is happening. Notice that when we had 0.3 repeated, right, what was our answer? Our answer was 1/3. But, watch, if I take 3, right, and divide it by 9, don't I get the same thing? 1/3? Okay, so take 0.244, and then take that 24, and instead of putting it over 9, put it over 99. And you get that's this, and it's 0.242424. So if you want to do 0.371, 3 of them forever, type into your calculator 371 over 999. and you would get the same thing. You would get that. Now, look, this is just to show you there's a format, a pattern to it, right? So the most challenging problem, and one that you would see more like on a test, is like this. And it's in your homework, and I'll let you do it on your own. But when you do something like that, you can't do something quick and easy like this to get the answer. All right? So notice a couple of things about this one. The 2 is first, right? The 2's not in the pattern. Point, and there's a 0 first, and then 1, 4, 1, 4, 1, 4. So the way we break this up, 2 plus 0.014 plus 0.00014. Is that going to be right? See this? Yes? And then I'm going to let you do it. I do it in the homework video, and you can watch me do it. But this is more involved. Okay, there's a lot more involved here. So please, if you get stuck, let me know. Watch the video. The last thing that I'll mention here is a classic problem of what is 0.999 forever equal to. Rewrite that as a fraction. If you follow what I just said, like for 0.244 forever, I said, what did you have to do? Rewrite it as 24 over 99? It would just be 1, wouldn't it? Do you think that 0.99 repeating forever is 1? Is it the number right next to 1?
Uncomfortably close to 1.
Uncomfortably close to 1?
Like coming into the urinal, going next to you when there's a bunch of others. That's how close he is.
That's how uncomfortable it is. Okay. What do y'all think about that? Look, if I have the number 1 here, and you're saying that 0.999 forever is the number right next to it, right? Can't I always find a number between any two numbers? Look, if you give me 2 numbers on a number line, I'm just going to pick them, 5 and 8. I can always pick a number. I can always find a number between them, guaranteed. Here's how I do it. I add the 2 numbers together and I divide by 2. That gives me their average. So what's this added together? 13 over 2, which is 6.5? 6.5 is the number right in the middle. So if you say that 0.99999 forever and 1 are 2 different numbers, then I'm going to be able to find one right in between it by taking the 2, adding the 2, dividing by 2. And so that cannot possibly be the number closest to 1. It actually is the number 1. That is the number 1. You've just never seen it written that way. I know it doesn't make sense, but it is. Okay? It is. There is no number that you can find between this and 1. There is no number there. All right? Now we can do this several ways to prove it. You could write it out as a geometric series, 0.9 plus 0.909 plus 0.009, and do everything we just did. And when you do all that, you're going to get a over 1 minus r, and it's going to turn out to be 1. Or I can try something that doesn't require as much work. Maybe I can convince you, maybe I can't. Maybe I won't. Let's call that x. Everyone ready? This is just for fun. All right? If that's x, everyone tell me what 10x is. What do you do when you multiply a decimal times 10? Move the decimal point over. So what is this? 9.999? Forever? Still? Okay, let me ask you this. Purely algebraically speaking, what's 10x take away x? 9? 9x? Do you agree? Okay, but what's 10x here? 9.999. Repeat it forever. Take away what's x up here? 0.999 forever. And what's this minus this? 9. So you're telling me that if x is this, then 10x is this. And 10x minus x is 9x. But that it has to be equal to this, right? This is 10x minus x. So you're telling me that 9x has to equal 9, right? Which means x has to be 1. Which means that this had to be 1 to start with. Okay, anyway.
Did you just solve the debt, U.S. debt problem?
That's it right there. That math is math I can't do. All right. So you're either going to believe that or you're not.
You can't pay for anything like that.
No, you're right.
You can't walk up to the clerk and be like, here's
Do you agree that that's the number 0? I mean, right? No? That's the number 0. That's pretty much what we are doing, but on the other end of it. This is the number that would be as close to 0 as you possibly could get. Because see, if I go way out here, I put a 1, then that's really close to 0, but it's not, right? But if I keep going with zeros, then it's just 0, right? Well, the 0.99 is getting you closer and closer to 1, but if you keep going forever, it is 1. It's a weird concept. Okay, one more series, so at least we can talk about it, be done with it, and then we'll pick up next class. We'll still have some way to go here in 8.2. Harmonic series. Harmonic series are not that bad. Okay, I think you'll like them. Because all harmonic series diverge, always. You just have to recognize that you have a harmonic series. That's all you have to do. So all harmonic series look like this. Sum n equals 1 to infinity of 1 over n. In fact, we can generalize this. This can become more general. The more general form of this, and the one that I'll use a lot in this class, is anytime you have a sum, really doesn't matter where we start here, but if you have a constant on top, and on the bottom you have a linear expression in the variable n, which is what we have here, isn't it? We have a constant on top. N by itself is n to the first power. That's linear, isn't it? It's not n squared. Okay. So if we ever see a constant, a number on top of a linear expression in n, we have got a harmonic series. And all harmonic series diverge. Would you like to see why? I mean, because we have to explain that's why we're here. All right, so why do these diverge? Let's write out this series right here. This is the series 1 plus a half plus a third. I think I started the class with this, didn't I? Okay, so why does this thing diverge? Let's see. What I'm going to do is I'm going to write out a bunch of these, all right? Let me write out a bunch of these. So I'm going to erase this to give myself a little more room. That series is 1 plus a half plus a third plus a fourth plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9. I don't know. I think, how far do I want to go? I'm going to go to the 16th. 1/10th, 1/11th, 12th, 13th, 14th, 15th, 16th. For homework, I'd like you to go out to 1,000,000. Just write that down. All right.
That'd be a bonus.
That'll be a bonus. I'll see you next semester when you're done.
How much?
All right. So this is the harmonic series, right? Yeah? I'm about to show you that this harmonic series is greater than infinity or equal to infinity. All right? So that's going to force, I'm going to show you that this sum right here adds up to be something that's greater than infinity. So what I'm going to do is I'm going to take these two numbers right here. So ignore the 1, ignore the 1/2. I mean, they're there, but don't worry about looking at them. Put those two numbers together, add those two fractions together. What's 1/3 plus 1/4? 7/12. Now we might need someone with a calculator for the next one. Don't take the next 2 and add them together. I want you to take the next 4 and add them together. Anyone have a calculator that can do that quickly? And I'm looking for it as a fraction. Or a decimal, it doesn't matter.
533 over 840.
533 over 840. All right, can you give me that as a decimal?
0.634.
0.634, something like that?
And then there is like a big number, and then there's that dash on top of it.
Okay, no, this is fine. This is what I was hoping for, something like that. 7/12, go ahead and give me that as a decimal too.
0.583.
0.583.
And then there's a dash on top of it.
Okay, so that's okay. We'll just take those. Now, I ignored the first, I ignored the 1/2. I did the first 2, added them together. Then I took the next 4, added them together. Guess what I'm going to take next? The next 8 and add them together. And when I do this, well, you know what? Maybe we don't need to add it up. Check this out for a second. Would you agree this is the smallest number in this list? Okay? This is the smallest number in this list. So this is bigger than 1/16. This is bigger than 1/16. This is bigger than 1/16. All of these? How many of these are there? 1, 2, 3, 4, 5, 6, 7, 8. So isn't this right here bigger than 8/16? Right? 1/16, 1/16, all, if there were 8 1/16, this would be 8/16. But this is bigger than that. I could have used the same logic here. What's the smallest number in this list? 1/8. How many of them are there? 4. So this is definitely bigger than how many eighths? 4/8. And then this right here, same logic. 1/4 is the smallest number. How many of them are in the list? 2. So this is definitely bigger than 2/4. What do all these have in common? They're all 1/2, right? So if I continue in my list and I go out and I take my next how many? Not 8, but take the next 16, I can be sure that they're all great, that those added up should be greater than what? What do you think? 16/32. And then if I take the next 32, I should be able to say they're all greater than 32/64. And I could do that indefinitely forever. So what I'm saying is that this sum right here is bigger than, right? All that is bigger than having a 1 plus a 1/2 plus a 1/2 plus a 1/2 plus a 1/2 plus a 1/2. Just a bunch of 1/2s together, right? Are y'all following? No, I felt like I lost you there. This is bigger than a 1/2, right? So the things I'm trying to match up, these are the same. These are the same. This right here is bigger than that, right? That's why I'm saying this sum is bigger than this. The next group of 4 is bigger than another 1/2. And the next group of 8 is bigger than the next 1/2. And the next one and the next one. But this is just 1/2s forever. And what's a 1/2 on top of a 1/2 on top of a 1/2 on top of a 1/2? Added up. Infinite. This is basically infinity, right? This one right here is going to infinity. So our sum has to be bigger than infinity, so it must be infinity itself. All harmonic series diverge. That's the best kind of proof I can show, all right? I hope you buy that. Okay? So I'll give you an example of something you would see on an assignment, right? Like, so does this converge or diverge? Converge or diverge? But now I'm talking about a series, not a sequence. Sum n equals 1 to infinity of 3 over, are you adding up all those numbers to infinity? Calm down, Ron. Calm down, Ron. Getting close? Halfway there? All right, is this geometric? What tells us geometric? What's usually the most important thing that we want to see with geometric? The n has got to be in the power somewhere, which it's not, right? So the only other thing now that we have is harmonic. And for harmonic, we're looking for a constant over a linear expression, which we have, right? This is a constant. This is a linear expression in n. This is harmonic. We're done. Harmonic, therefore, diverges. Here's what a student will do on a test, is they'll tell me for some reason that this converges to 0. What did they do? They took the limit as n went to infinity, and they found out that that sequence goes to 0, which I completely agree with, but that doesn't mean that the series goes to 0, right?
How would you know if you're looking for a series or non-series?
Right here, this notation. If I say, does this converge or diverge, and I give you the series with this notation, then you know I'm looking at that, right? In contrast, if I gave you this, I would ask you converge or diverge, and I put a sub n is what, 3 over 4n plus 1? Then you just let n go to infinity there. Last thing, I've got 4 minutes, and I have enough time to show you one last thing. Is harmonic okay? Yeah. All right. So look, we have so far a geometric series which requires some work. We've got the harmonic, which requires just identification. And then things are going to start to get more complicated. So we start to have a list of tests that we're going to be using to try and help us figure out if these series converge or diverge. If it's geometric, we'll be happy. If it's harmonic, we'll be happy, but a lot of them aren't. So the first test, in the next class, I'll hand you a list of the tests. The first test that we have is what's called the Nth Term Test. This is our first of a few tests. And here's what it says. Given what is that? Yeah, just given an infinite series, right? Someone gives you an infinite series. If the limit as n goes to infinity of a sub n does not equal 0, then the series diverges. So let's translate this in the last 2.5 minutes I have. Someone gives you a series. If you look at the sequence and take its limit, if that does not go to 0, you're guaranteed divergence of the series. If it doesn't go to 0, you're guaranteed divergence. The thing you have to be very careful with on this is what happens if you look at the inside and the inside does go to 0? What does that tell you? Convergence? It actually tells you nothing. And that's where people mess this Nth term test up. Think about the logic of things. If all of these guys in here, right, as you wrote these out, A1 plus A2 plus A3, if each of these guys is not getting smaller, they're all getting closer to a number. Let's say like they're all getting closer to 1/2. Then wouldn't it just be like adding up 1/2 plus 1/2 plus 1/2 forever? And that would overflow. For convergence, we have to at least have that these are going to 0. So if they aren't going to 0, it diverges. Understand? Understand? That's the first test we always want to do if we're in trouble, if we can't figure out what's going on. Take this limit, hope that it's not 0. If it's 0, you're going to have to move on to the next test. Let me show you in the last 1 minute 2 different series next to each other and how you could improperly use this test. So look at this one. N equals 1 to infinity, 1 to the n, versus n equals 1 to infinity of 1/10 to the n minus 1. The one on the left is what type of series? Harmonic. The one on the right? Geometric. We know what happens here, don't we? This does what? Diverges. This one converges because r is what? 1/10? So this is a convergent. This is divergent. Everyone agree? Now let's see someone screw up the nth term test. They come in here and they say nth term test. They take the limit as n goes to infinity of this one. 1 over n, and they get what? 0. And they go, shit, yeah, that means it converges. No, that's not what it means. It means that you don't know anything. Does that make sense? You don't know. It could converge, it could diverge. The only thing the nth term test is good for is if this thing came out to be 1, then you could say it diverged. You could almost call the nth term test a test for divergence to kind of help you see that that test only tells you one thing, divergence, and that's it. Understand? We'll practice with this more. Now, what if you did this one right here? Limit n goes to infinity of 1/10 to the n minus 1. So just take that. What do we say happens if you take a number that's smaller than 1? It gets big, so it gets smaller, right? This goes to 0 too. And so you go, yeah, it converges. Well, you got lucky. It does converge, but this test didn't tell you that. You just got lucky. You see what I'm saying? Just because the inside piece goes to 0 does not mean it converges. There's an example of one that diverges. There's an example of one that converges. Yes?
Why do you have n goes to 0 and not n goes to infinity?
I don't know what you're talking about. No idea what you're talking about. Have you checked into glasses? You haven't looked at glasses yet? We're done. The homework assignment for this, you can't do it all, but I can tell you at least what you can do at this point. This is off of page 443. Seven through 12, 23, and 24, 31 through 34. Those are just all of them. Now, like I said, I've done the video for all of the homework for the entire section for 8.2. It's already online. But this is not the entire assignment. We still have not covered enough of this nth term test in action, and we haven't covered what are called collapsing series. So we'll do that next time. More nth term test, collapsing series, then we move into 8.3. Have a good weekend, I guess. Catch up. Don't be behind on Tuesday, all right? You got the whole weekend. I know you got nothing else going on.